by using something called a band gap reference. So we won't be going into the details of this. So in this course, so it will be taught in the next in your fourth year, those who will be taking this. What we will be discussing is once we have a precision current source, how do we realize millions of copies of these, millions of current sources using that? Because building a precise current source, millions of them, this circuit is pretty intense. Okay, this requires an op amp, this requires feedback, this requires diodes, so all kinds of things, because this requires an op amp, then diodes, resistors, and you have to use feedback. Negative feedback. So it is pretty intensive. So you cannot build millions of these, and they take up a lot of area and all. Sometimes these also, not only is it intensive, these also have startup issue. You power on the chip, gone. It's not giving you the current source. So somebody has raised a hand. Who is it? Who is it? How come I am not able to see? Nandaram Prajapati. Yes, please tell me. Nandaram, you have raised your hand.
Sir, mistakes हो गया.
Oh, अच्छा, कोई problem नहीं. Okay. So therefore, these are startup issue. What it means is that when you power on the chip, it is gone. Either the output of this is either supply voltage or ground, and there is no current coming. There is nothing. So this is a startup issue. So you have to spend a lot of time when you are trying to realize this. Besides startup issue, it might be very sensitive to. Sometimes what happens is that when you do a temperature cycle, you go from 0 degree to 85 degrees and suddenly come down back to 0 degree, boom, this thing crashes. I have seen this problem in one of the chips, and it took us more than a month to figure out why it was happening. It was happening, the chip went to Motorola. Motorola was using this, and they said that they were using this thing in inside the house, and it was very cold outside. It was winter season, so they were using it inside the house because of some. It was a modem. It was a cable modem receiver. Okay, so they're using it inside the house, and for some reason they had to take it inside the lab, Motorola labs, and some reason they wanted to see how the characteristic is outside, in the outside thing, if I increase the cable length to a certain extent, and they did that, and that resulted they had to go outside, and outside was minus 20 degrees Fahrenheit. Okay, so close to you can see F minus 32 divided by 2 is your thing in centigrade. So it goes to minus 25 degrees centigrade roughly. It was outside, it was minus 25. So it went inside in the room when it was working, it was pretty hot. It heated up, the chip was on, it was burning current, so it went up to 85 degrees. And as soon as it came back down, went outside, suddenly the temperature dropped to 0 degree, because outside ambient temperature is minus 25 degrees C. Okay, so it suddenly went down to 0 degree, and boom, the thing didn't work at all. We were not receiving any signal. Okay, no, TV was dead. Okay, so then Motorola got back to us, and it took us quite some time to go to the lab. We went to the lab and did this temperature cycling in the lab. You have temp chambers in which you can do the temperature cycling. We replicated this happening. Then we replicated, pinpointed to which part of the circuit it was getting a problem. From there, we found out actually it was a simple current source that was giving this problem. And then we had to come up with a fix. We did a lot of simulations and convinced Motorola. The next chip came back, and they did this temperature cycling, and in fact they went all the way down to minus 40 degrees also. From 0 to 125 degrees they went, and down back to minus 40 degrees Celsius, and it was all fine. Okay, so so these band gaps have all these issues. They have temperature cycling issues and all. So instead of doing that, we build one band gap, we simulate and beat the hell out of it and make sure it works across all these cases. And then we take that current, precise current, and replicate it millions of times to realize your current source. For example, your HD TV, which is 1920 cross 1080, 1920 cross 1080. How many? It is 2 mega current sources are there, 2 million current sources are there, right there. So you have to, because that's a DAC. So you need these current sources. So we'll discuss how to, so this copying millions of current sources is done using something called current mirrors. Okay, precisely a precision current source. Okay, so now that's the motivation of why we are studying this. Now I'll discuss some impractical realization of current sources. Okay, somebody will say that I will build a current source. You have the supply voltage. We'll use this. Okay, so this is Q1, this is R1 and R2 plus minus VBE. So this is an impractical, we are first realizing current sources. This is a true current source. There is nothing, as long as this is in forward active region, this behaves like a current source and gives a current I, which is a function of VB. But why is it not a precise current source? Is because if VCC changes, which happens, for example, you take your Bluetooth mouse, okay, you put the battery in it. When you have the battery, it is 1.2 volts. VCC equal to 1.2 volts. And after 2 months, this will drop down to 0.9 volts. So if this drops down, then this voltage is going to change, and if this voltage changes, this current is going to change. So therefore, this is not a practical current source. Similarly, if I build millions of these R1 and R2 will have the tolerances. You have studied that okay. These tolerances will affect the current, so they won't be precise current sources. The similar, the MOS counterpart of this is going to be, let's call this like this. Okay, plus minus VGS. Okay, so this is, so here the current that we are getting is given by R2 divided by R1 plus R2 times VCC equal to VT ln I1 by IS. This is VBE, and this is this thing, and here it is R2 by R1 plus R2 by VDD equal to square root of twice I1 by mu n Cox W over L plus VTH. Okay, so this is the see. So now here you can clearly see that if VCC changes, my current is going to change. Similarly, VDD changes. Similarly, if the ratio of this changes due to variation in R1 and R2, it will change. And therefore, also if the W over L changes, it is going to change. It is going to vary, because if you are going to have build so many of them, you will have a lot of problems. So that's why we do not go for current source realization using this. We realize them using band gap circuits. Band gap circuits. Okay. Okay, so now, so we have now so that means we will have band gap circuit gives you, so it gives you an IREF. Okay, this is a current, this is a source. Okay, if it is coming from VDD. Okay, this is a source. If it is going to ground, it is called a sink. Okay, so a source comes from the supply and sink goes to the ground. So we will have these two things. Okay, so please make sure that you know that source and a sink. Okay, now So what we do is we will put in this. So I'll take a source IREF and give it to a mirroring circuitry. We call this as a current mirror. And then we get I copy. Okay, we get this I copy. Now, what is the simplest way of making this copy? Is so we have IREF, and what will be the circuitry that we put in here that can be used to give me I copy. So the simplest circuit that we can have is nothing but a diode connected. So this circuit is going to, so I can have a diode connected device. So the current flowing through this device is a function of VBE, and exactly same VBE is maintained across this. So therefore this makes a exact copy of the almost I copy will almost be equal to IREF. We'll tell you why almost we are putting. Okay. And the same thing can be done. The MOSFET counterpart is going to be exactly the same thing. IREF. So you have this thing. Okay. So this is there. So this I copy will almost be equal to IREF. Okay. Now this one is therefore, yes.
Sir, what is IREF actually?
IREF is the reference current that we are copying millions of times. That's what we discussed, right?
So like where it is coming from?
I discussed that here, right? This is IREF is building a precise current source is beyond the scope of this course. It is done by using something called a band gap. So now this is a current source. Sink here to be more precise. We can build a current source as well. Now we instead of building a current, this is not a good current source. So what we do is we realize using band gap, we realize something called a precise current source, which is beyond the scope of this course. And this band gap circuit gives you IREF, a golden current source. Okay, and if it is supplying current from the supply, we call it as a source. If it is sinking to the ground, we call it as the sink. Does it make sense?
Yes, I got it.
Okay. Somebody had a chat, something came in the chat, so I don't know. Did somebody put something in the chat? Okay. Okay. So now this is the copy, I copy. So what you do is you assume that you have, for this course, assume that you have been given a reference, golden reference. Okay. By using a, somebody designed it and gave it to you. It says that this gives you 1 milliamp in period. It gives you 1 milliamp. It won't budge from that 1 milliamp, even if the temperature changes from -40 to 125. Okay. It will give you exactly 1 milliamp, exactly 1 milliamp. What you do is now you have to generate millions of copies of that 1 milliamp. You can do it using this. This circuitry is called the mirroring circuitry. This is called the mirror, or to be more precise, current mirror. So this is also, this is the precise current mirror. Okay, MOS current mirror. Okay. Okay. So again, now.
Sir, in case of MOS, the I copy is actually equal to IREF, right?
We will get there. So let me first define. Uh, now we will, now first of all, when you design a current source, What is an ideal current source? R out tends to infinity, right? An ideal current source will have a R out infinity, right? And voltage across the current source, V current source, should be equal to 0. That means if I have a current source and I copy is behaving like a current source, what does the VI characteristic of this look like? No matter what is the voltage you apply, it should stay constant. That means R out is infinity. With 0 voltage also it gives you this current. Now keep in mind this I copy that we have done is providing current to some circuitry. Okay, some op amp or some other transistor or making it flow through a resistor or whatever it is. So any voltage drop across this is going to reduce the swing in the main circuitry. This is just providing the current, right? So any drop across this, so we call that the voltage across the current source is called the compliance voltage. So compliance voltage is the minimum voltage across the current source which makes sure that it behaves like a true current source, behaves like a current source. So so now if I draw the VI characteristic of a MOSFET, that means I'll draw VDS. So it will behave like a current source only at VD-SAT. And you know exactly what is VD-SAT, and other names of VD-SAT are V overdrive voltage or V effective voltage. So it is not flat like this. So you need a minimum voltage across the VDS, and this is the current flowing through the transistor. In case of a BJT, what happens? So this is for a MOSFET. Okay. In case of a BJT, what happens? VCE, and here it is going to behave like a current source at VCE SAT, and that SAT is roughly equal to 0.2 volts. Okay. Okay, it is 0.2 volts. So that means the compliance voltage for a MOS current source is VD-SAT, and for a BJT current source is 0.2 volts. Now lower the compliance voltage, the larger is the swing of the circuit, larger is the swing of the circuit. So to give you an example, suppose I build a current source loaded common source amplifier. Okay, so V in is applied here and you have a bias voltage here and we have V out. Okay, we have V out here. What will be the swing here? The maximum voltage that this V out can reach is equal to VDD. So V out max equal to VDD minus VD SAT. And this is a current source. So M1 and M2. M2 is a current source. So if M2 is small, if the VD SAT is smaller, means this behaves like a current source with smaller compliance voltage, you get larger swing in the circuit. I hope this statement is clear. Lower the compliance voltage, the larger is the swing of the circuit. Okay, so this is very, very important for you to understand that. So that means we want to make sure that the current source that we build realize after copying means now this becomes this we have copied these currents, and these copied currents are these are behaving like current sinks. In this case we can build current sources. I'll show that. So these current sinks should have low compliance voltage. Okay, next. Now it should have R out equal to infinity. And the third thing, what do we want? When mirroring accuracy should be 100%. Okay, mirroring accuracy should be 100%. So three things quantify a current mirror: output impedance, VCS, V between voltage, compliance voltage of the current source, and the accuracy of mirroring. So you want to make this go as high as possible, make this compliance voltage as low as possible, and you want this to be 100%. Am I clear with this? Is that clear? Okay. So now next thing is that so we want to mirror currents. Okay. We want to mirror currents using BJT, let's say, MOSFET. But suppose this is Iref, okay? To flow Iref, I need a certain W over L. I want the mirror should carry twice Iref. Then what do? You put two W by L's in parallel. Two transistors in parallel gives you twice Iref. If I want to put M such things in parallel, so this is 1, 2, M such things in parallel, I will get M times Iref. Okay, so that means I can do multiplication of currents. Now, if I have a current source, here I am building all these as current sinks. How do I build a current mirror with sources? These are all sinks. These are all sinks. So what the way to do that thing is you build it like this, because you are given this, somebody has given you this golden reference. So you take this W by L and this thing, you take it this way, and you have a current I copy. Okay, so if I make this W by L, then exactly I copy. So I copy will roughly be equal to Iref. If this is WP by LP, I'm giving a notation for PMOS WP and NMOS W and L. Okay, I keep this thing. This will roughly be equal to. We'll analyze the accuracy. Okay, so this becomes a source. So all I need is one golden current reference, which I painstakingly build it, and then I can do a copying and do whatever I want and get whatever this thing. The same thing can be if I replace this with a BJT. I can replace this with a BJT. Okay, and BJT, the current is proportional to the emitter area AE. So here I can have multiple copies of the BJT, with area AE. Okay, and then you can exactly get the same. You can get M times Iref. So you replace this MOSFET with the BJT with certain area. you put these replace these MOSFETs with BJTs of area AE, M of them, and you get M times IREF. And here again you replace this with a BJT, replace this with a BJT, replace this with a PNP. These two will be NPNs. Okay, this will be PNP, this will be PNP. You realize a current source. Am I clear? Okay, is that clear? Okay. Any questions? So I'll stop at this point.